Municipal water treatment relies heavily on liquid aluminum sulfate to pull suspended solids out of solution and purify drinking water at a massive scale. Today, we are going to master the precision jar test. We'll determine the exact optimal dose for your plant and troubleshoot floc failure when cold winter weather disrupts your chemistry. Before touching the stirring apparatus, you need to establish a strict baseline. Gather at least a 6.5-liter raw water sample, prepare a 1% or 10,000 milligrams per liter alum solution, and log your plant's current flow rate. Locking in these precise parameters in the lab allows us to scale our math up to millions of gallons later, avoiding massive chemical waste and preventing poorly treated water from reaching the filters. Operators generally rely on two chemical tools. Primary coagulants destabilize particles so they can clump together. Coagulant aids are then added to act like a dense net, maintaining that floc formation and pulling those clumps downward. If you're applying alum at low doses, typically under 5 milligrams per liter, the primary mechanism is charge neutralization. Positively charged alum ions attach to negatively charged dirt particles, canceling each other out. At higher doses, the chemistry shifts to entrapment. Aluminum hydroxide precipitates into a physical web, forming a sweep floc that actively captures suspended solids as it sinks. To simulate these specific mechanisms accurately, you need specialized laboratory equipment. A variable speed steering apparatus and a diffused light box are critical. You also need a row of 4 to 6 1-liter jars, precision lab pipettes, a digital tiner, and a turbidity meter to record fine distinctions between your samples. Because different doses trigger entirely different chemical thresholds, artificially forming and protecting stable floc in a lab requires precise variable speed control. Start your test by placing exactly 1 liter of raw water into each of your jars. Next, prepare your graduated doses of liquid alum. To generate valid comparative data, you must inject these doses at the exact same moment. Immediately trigger the flash mix phase. Run the stirring blades at a rapid 100 RPM to violently agitate the water and instantly initiate charge neutralization. After the initial flash, drop the speed to approximately 5 RPM. This slow mix phase allows the delicate floc to collide and grow large enough to settle out without being sheared apart by the blades. Now, completely stop the rotation and allow the jars to sit completely undisturbed for 15 to 20 minutes. Carefully extract a test sample using a syringe. Pull your water from exactly 1 inch below the surface so you don't disturb the settled floc layer at the bottom. By matching your lab's flash and slow mixing times to the actual flow rate of your plant's clarifier, the resulting sample data becomes a highly accurate predictor of full-scale performance. Run your extracted samples through the turbidity meter. You want to record these readings at specific intervals, typically 2.5, 5, 10, 15, and 25 minutes into the test run. This graph plots the resulting turbidity in NTU on the vertical axis against your alum dose on the horizontal axis. The lowest point on the curve clearly identifies your optimal dose. However, winter temperatures drop near 0 degrees Celsius, increasing viscosity. This applies greater shear force to particles, cutting the alum hydrolysis rate in half. This cold water shear force prevents the particles from binding, creating a broken, loose floc that simply will not settle to the bottom. When standard alum chemistry fails in low temperatures, you have to adjust. Switch to a high basicity polymer like PaCl, or introduce coagulant aids to force proper floc formation. A graph is only useful if you know how to interpret the environmental variables behind it, giving you the confidence to override standard protocols when the raw water demands it. Once you have your verified data, it's time to take the solution out of the laboratory and apply it to the massive settling tanks outside. Take the optimal milligram per liter dose from your graph and translate it directly into your plant's chemical feed pump settings. Document these precise steps into formal standard operating procedures. This ensures your entire team can rapidly adapt the plant when sudden temperature drops occur. Mastering the jar test replaces reactive guesswork with proactive, optimized science. You ensure proper filter performance, control your chemical costs, and guarantee safe, clean water.